Julian day is the continuous count of days since the beginning of the Julian period, used primarily by astronomers. The Julian day number is the integer assigned to a whole solar day in the Julian day count starting from noon Greenwich Mean Time, with Julian day number 0 assigned to the day starting at noon on January 1, 4713 BC, proleptic Julian calendar, a date at which 3 multi-year cycles started and which preceded any historical dates. For example, the Julian day number for the day starting at 1200 on January 1, 2000, was 2,451,545. The Julian date of any instant is the Julian day number for the preceding noon in Greenwich Mean Time plus the fraction of the day since that instant. Julian dates are expressed as a Julian day number with a decimal fraction added. For example, the Julian date for 003000 at January 1, 2013, is 2,456,293.520833. The Julian period is a chronological interval of 7,980 years beginning 4713 BC. It has been used by historians since its introduction in 1583 to convert between different calendars. 2015 is year 6728 of the current Julian period. The next Julian period begins in the year 3268 AD. Terminology. The term Julian date may also refer, outside of astronomy, to the day of year number in the Gregorian calendar, especially in computer programming, the military and the food industry, or it may refer to dates in the Julian calendar. For example, if a given Julian date is October 5, 1582, this means that date in the Julian calendar, outside of an astronomical or historical context. If a given Julian date is 40, this most likely means the 40th day of a given Gregorian year, namely February 9th. But the potential for mistaking a Julian date of 40 to mean an astronomical Julian day number is justification for preferring the terms ordinal date or day of year instead. In contexts where a Julian date means simply an ordinal date, calendars of a Gregorian year with formatting for ordinal dates are often called Julian calendars. In spite of the potential for misinterpreting this as meaning that the calendars are of years in the Julian calendar system, historical Julian dates were recorded relative to GMT or ephemeris time, but the International Astronomical Union now recommends that Julian dates be specified in terrestrial time, and that when necessary to specify Julian dates using a different time scale, that the time scale used be indicated when required, such as JD. The fraction of the day is found by converting the number of hours, minutes, and seconds after noon into the equivalent decimal fraction. Time intervals calculated from differences of Julian dates specified in non-uniform timescales, such as Coordinated Universal Time, may need to be corrected for changes in time scales. Variants. Because the starting point or reference epoch is so long ago, numbers in the Julian day can be quite large and cumbersome. A more recent starting point is sometimes used, for instance by dropping the leading digits, in order to fit into limited computer memory with an adequate amount of precision. In the following table, times are given in 24-hour notation. In the table below, epoch refers to the point in time used to set the origin where explicitly indicated, of the alternative convention being discussed in that row. The date given is a Gregorian calendar date if it is October 15, 1582, or later, but a Julian calendar date if it is earlier. JD stands for Julian date. 0H is 0000 midnight, 12H is 1200 noon, at unless otherwise specified. The modified Julian date was introduced by the Smithsonian Astrophysical Observatory in 1957 to record the orbit of Sputnik via an IBM 704 using only 18 bits until August 7, 2576. MJD is the epoch of AX, VMS and its successor Open EVMs, using 63-bit date time, which allows times to be stored up to July 31, 31086, 248, 547. The MJD has a starting point of midnight on November 17, 1858 and is computed by MJD equals JD 2,400,000.5. The truncated Julian day was introduced by NASA Goddard in 1979 as part of a parallel grouped binary timecode designed specifically, although not exclusively, for spacecraft applications. TJD was a 4-digit day count from MJD 40,000, which was May 24, 1968, represented as a 14-bit binary number. Since this code was limited to 4 digits, TJD recycled to 0 on MJD 50,000, or October 10, 1995, which gives a long ambiguity period of 27.4 years. Only whole days are represented. Time of day is expressed by a count of seconds of a day, plus optional milliseconds, microseconds and nanoseconds in separate fields. Later PB5J was introduced, which increased the TJD field to 16 bits, allowing values up to 65,535, which will occur in the year 2147. There are 5 digits recorded after TJD 9999. The Dublin Julian date is the number of days that has elapsed since the epoch of the solar and lunar ephemerides used from 1900 through 1983. Newcomb's Tables of the Sun and Ernest W. Brown's Tables of the Motion of the Moon. This epoch was Noonut on January 0, 1900, which is the same as Noonut on December 31, 1899. The DJD was defined by the International Astronomical Union at their meeting in Dublin, Ireland, in 1955. The Lilian day number is a count of days of the Gregorian calendar and not defined relative to the Julian date. It is an integer applied to a whole day. Day 1 was October 15, 1582, which was the day the Gregorian calendar went into effect. The original paper defining it makes no mention of the time zone, and no mention of time of day. It was named for Aloysius Lilius, the principal author of the Gregorian calendar. Rata die is a system used in RexX, Go and Microsoft .NET. It uses the local time zone, and day 1 is January 1, that is, the first day of the Christian or Common Era in the proleptic Gregorian calendar. The heliocentric Julian day is the same as the Julian day, but adjusted to the frame of reference of the Sun, and thus can differ from the Julian day by as much as 8.3 minutes, that being the time it takes the Sun's light to reach Earth. To illustrate the ambiguity that could arise, consider the 2 separate astronomical measurements of an astronomical object from the Earth. Assume that 3 objects, the Earth, the Sun, and the astronomical objects targeted, that is, whose distance is to be measured, happen to be in a straight line for both measures. However, for the first measurement, the Earth is between the Sun and the targeted object, and for the second, the Earth is on the opposite side of the Sun from that object. Then, the 2 measurements would differ by about 1,000 light-seconds. For the first measurement, the Earth is roughly 500 light-seconds closer to the target than the Sun, and roughly 500 light-seconds further from the target astronomical object than the Sun for the second measure. An error of about 1,000 light-seconds is over 1% of a light day, which can be a significant error when measuring temporal phenomena for short-period astronomical objects over long time intervals. To clarify this issue, the ordinary Julian day is sometimes referred to as the geocentric Julian day in order to distinguish it from HJD. History. The Julian day number is based on the Julian period proposed by Joseph Scaliger in 1583, at the time of the Gregorian calendar reform. as it is the least common multiple of 3 calendar cycles used with the Julian calendar. 15 times 19 times 28 equals 7,980 years. Its epoch falls at the last time when all 3 cycles were in their first year together. Scaliger chose this because it preceded all historical dates. Years of the Julian period are counted from this year 4713 BC, which was chosen to be before any historical record, since it is now certain that every possible combination of the 3 cyclic numbers finds its place in the Julian period. It is evident that the first year of the Christian era, which was the 10th year of a solar cycle, the 2nd of a lunar cycle, and the 4th of a cycle of indiction, finds its place within this artificial era, and must answer to that particular year of the period which is characterized by the same cyclic numbers. Hence, to refer the Christian era to the Julian period is the same thing as to find out what year of that period it is, which, when divided by 28 will leave a remainder 10, divided by 19 will leave a remainder 2, and divided by 15 will leave a remainder 4. The solution of this problem belongs to the higher mathematics, by which it is found that the year required is the 4714th of the period in question. Hence dual per 4714 equals AD 1, and consequently Julian period 4713 equals BC 1. In point of fact, finding the year is a very straightforward arithmetical procedure. See calculation below. Although many references say that the Julian in Julian period refers to Scaliger's father, Julius Scaliger. In the introduction to Book V of his Opus De Remendatione Temporum he states, Julianum vocavimus, quia ad annum Julianum dum taxit accommodator est, which translates more or less as, we have called it Julian merely because it is accommodated to the Julian year. Thus Julian refers to Julius Caesar, who introduced the Julian calendar in 46 BC. Originally the Julian period was used only to count years, and the Julian calendar was used to express historical dates within years. In his book Outlines of Astronomy, first published in 1849, the astronomer John Herschel added the counting of days elapsed from the beginning of the Julian period. The period thus arising of 7,980 Julian years is called the Julian period, and it has been found so useful. We owe its invention or revival to Joseph Scaliger, who is said to have received it from the Greeks of Constantinople. The first year of the current Julian period, or that of which the number in each of the 3 subordinate cycles is 1, was the year 4713 BC. And the noon of the 1st of January of that year, for the meridian of Alexandria, is the chronological epoch, to which all historical eras are most readily and intelligibly referred. By computing the number of integer days intervening between that epoch and the noon of the day, which is reckoned to be the first of the particular era in question, the meridian of Alexandria is chosen as that to which Ptolemy refers the commencement of the era of Nabonassar, the basis of all his calculations. Astronomers adopted Herschel's days of the Julian period in the late 19th century, but used the meridian of Greenwich instead of Alexandria, after the former was adopted as the prime meridian after the International Meridian Conference in Washington in 1884. This has now become the standard system of Julian days, numbers. The French mathematician and astronomer Pierre-Simon Laplace first expressed the time of day as a decimal fraction added to calendar dates in his book, Traité de mécanique céleste, in 1799. Other astronomers added fractions of the date of the Julian day number to create Julian dates, which are typically used by astronomers to date astronomical observations, thus eliminating the complications resulting from using standard calendar periods like eras, years, or months. They were first introduced into variable star work by Edward Charles Pickering, of the Harvard College Observatory, in 1890. Julian days begin at noon because when Herschel recommended him, the astronomical day began at noon. The astronomical day had begun at noon ever since Ptolemy chose to begin the days in his astronomical periods at noon. He chose noon because the transit of the sun across the observer's meridian occurs at the same apparent time every day of the year, unlike sunrise or sunset, which vary by several hours. Midnight was not even considered because it could not be accurately determined using water clocks. Nevertheless, he double-dated most nighttime observations with both Egyptian days beginning at sunrise and Babylonian days beginning at sunset. This would seem to imply that his choice of noon was not, as is sometimes stated, made in order to allow all observations from a given night to be recorded with the same date. When this practice ended in 1925, it was decided to keep Julian days continuous with previous practice. Calculation. The Julian day number can be calculated using the following formulas. The months January to December are 1 to 12. For the year, astronomical year numbering is used. Thus 01 BC is 0, 02 BC is -1, and 4713 BC is -4712. D is the day of the month. JDN is the Julian date number, which pertains to the noon occurring in the corresponding calendar date. Converting Julian or Gregorian calendar date to Julian day number. The algorithm is valid at least for all positive Julian day numbers. The meaning of the variables are explained by the Computer Science Department of the University of Texas at San Antonio. It is worth noting that this algorithm does not follow the NASA or the U.S. Naval Observatory, the convention in these systems being that the Gregorian calendar did not exist before the date October 15, 1582. This algorithm effectively backdates the Gregorian calendar onto the Julian calendar for dates before the introduction of the Gregorian calendar. Thus, any calculations made with this formula before October 15, 1582, will not agree with these previous ephemerides. You must compute first the number of years and months since March 1 minus 4,800. The value will be 1 for January and February, and 0 for other months, and M will be 0 for March and 11 for February. All years in the BC era must be converted to astronomical years, so that 01 BC is year 0, 02 BC is year -1, etc. Convert to a negative number, then increment toward 0. Then, if starting from a Gregorian calendar date, compute. Otherwise, if starting from a Julian calendar date, compute. Note: 5 gives the number of days since March 1 and comes from the repetition of days in the month from March in groups of 5. Finding Julian date. Given Julian day number and time of day for the full Julian date. So, for example, January 1, 2000, at 12:00:00 corresponds to JD equals 2,451,545.0. Finding day of week. Given Julian day number, the U.S. day of the week W1 can be determined from the Julian day number J with the expression W1 equals mod. The ISO day of the week W0 can be determined from the Julian day number J with the expression W0 equals mod +1 Julian or Gregorian calendar from Julian day number. This is an algorithm by Richards to convert a Julian day number J to a date in the Gregorian calendar. Richards does not state which dates the algorithm is valid for. All variables are integer values, and the notation (divb) indicates integer division, and mod denotes the modulus operator. For Julian calendar, 1 f equals j plus j. For Gregorian calendar, 1 f equals j plus div 146,097 times 3 div 4 plus c. For Julian or Gregorian, continue. 2 e equals r times f plus v3. G equals mod div r4. H equals u times g plus w5. D equals div u plus 1 6. M equals mod plus 1 7. y equals y plus div and dm, and y are the numbers of the day, month, and year respectively. Julian period from Undiction, Metonic and solar cycles. Let y be the year BC or AD and I, M and S respectively its positions in the Undiction, Metonic and solar cycles. Divide 6916 I plus 4200 meters plus 4845 by 7980 and call the remainder R. If R greater than 4713, Y equals and is a year AD. If R less than 4714, Y equals and is a year BC. Example: I equals 8, M equals 2, S equals 8. What is the year? Equals 55,328, equals 8,400, equals 38,760. 55,328 plus 8,400 plus 38,760 equals 102,488. 102,488 7,980ths equals 12 remainder 6,728. Y equals AD 2015.